Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to Sridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our class 12th physics playlist, in chapter electromagnetism, we will study UCM, uniform circular motion in magnetic field. When a charged particle enters in magnetic field with 90-degree angle of velocity and magnetic field, we will discuss all type of exam pattern based on such circular motions, and we'll also study some numerical problems to enhance subject understanding. So let's start. Uniform circular and helical motion of charged particles in uniform magnetic field. Let's understand uniform circular motion, UCM, of a charged particle in magnetic field. A charged particle when moves in a magnetic field with velocity vector making an angle 90 degree with magnetic field, it will perform a circular motion, and in that the particle with same tangential velocity revolves around a central axial position with a constant radius due to balance of magnetic force exerted by magnetic field in the direction perpendicular to plane of velocity and magnetic field and the centripetal forces of circular motion. To find out direction of magnetic force on a moving positive charge, we use Fleming's left hand rule and stretch thumb, forefinger and middle finger mutually perpendicular as shown here, and the forefinger is directing towards the direction of magnetic field which is perpendicular to this screen plane and inward as shown by these crosses here. So this forefinger is in the direction of magnetic field. Now through raised elbow we can rotate our left hand such that the central finger get aligned with the direction of motion of positive charge, and in that case this thumb of left hand indicate the direction of magnetic force on moving positive charge in this inward directed perpendicular field, and when V and B both are perpendicular to each other and the particle got maximum QVB force directed inward, that force will deviate this particle, and displacement along velocity and force of magnetic field both remain perpendicular to each other, and force of magnetic field won't perform work on moving charge. So with same constant magnitude of tangential velocity, the force and acceleration change the direction of velocity to perform a circular motion. We can check the direction of force to some other positions. At this new position, this forefinger is in the direction of magnetic field inward, and we can rotate left hand such that middle finger get aligned with direction of velocity of positive charge. Then this thumb indicate the direction of force always towards a central position, and particle perform a circular motion. During this uniform circular motion, both angular velocity of particle and angular displacement remain along the axis of this circular motion, and axial direction of angular displacement and angular velocity is given by the thumb of right hand perpendicular to this plane of rotation when the finger of right hand are curled along the direction of rotation of particle. So here this positive charge moving in this velocity direction experience a perpendicular force, and when charge particle motion and magnetic field are perpendicular to each other and force magnitude is maximum QVB, particle perform a circular motion. Angular displacement and angular velocity for this anti-clockwise rotations are perpendicular to this plane along the thumb of right hand as denoted by dot here. In uniform circular motion, a particle with constant magnitude of velocity revolves around a periphery of a circle around a center position, and on circular periphery from one position to two position, this is tangential or linear displacement, and linear displacement from position 1 to position 2 at this center position generate an angle theta, and this theta is called as angular displacement, and angular displacement and linear displacement are related to radius of this circular motion, which is distance of circular periphery with the central axis of this rotation. In terms of vector notation, we can say linear tangential displacement is vector cross product of angular displacement and radial vector, and as per right hand corkscrew rule. For this anti-clockwise rotation, the direction of angular displacement along axis of rotation is upward to this plane as shown by this blue arrow, and this plane contain displacement vector and radial position vector are and the cross product of two is perpendicular to this plane given by the thumb of right hand when the finger are curled from angular displacement to radial vector as shown here in this black arrow direction along the instantaneous direction of velocity. Now when particle revolves during uniform circular motion, the rate of change of angular displacement with time is known as angular velocity, and angular velocity is also directed in the same direction as that of angular displacement, and in place of angular displacement we can write ratio of linear displacement to radius of circular motion, and rate of change of linear displacement with time is known as linear velocity. So angular velocity is given as linear velocity divided by a radius, and in vector notation we can say linear velocity is vector product of angular velocity vector and radius vector, and again this plane contain angular velocity vector and radius vector, and the cross product of two perpendicular to this plane given by right hand thumb when finger are curled from angular velocity to radius is in this black arrow direction is linear velocity. So linear velocity is cross product of angular velocity and radius vector. During uniform circular motion, the magnitude of velocity, that is speed, remains the same and particle rotates with constant radius circle. So its angular velocity remain constant. So there is no angular acceleration in uniform circular motion, but there exists radial acceleration, and due to magnetic force acting on this moving particle in magnetic field, the velocity will change in direction only from this one position to two position, and the change in velocity of one position and second position can be obtained by subtraction of first velocity from second position velocity, and for subtraction velocity vector is reversed and added. Then this become the difference of two velocity, and these two opposite angle theta is the same, and we know for small value of theta is arc by radius, arc is change in velocity and radius is velocity vector, and we know radial acceleration is the rate of change of velocity with respect to time, and in place of change in velocity we can write velocity multiplied by angular displacement, and rate of change of angular displacement with respect to time is known as angular velocity. So we can say the radial or linear acceleration which change the direction of velocity vector is equal to product of linear velocity and angular velocity, and in place of angular velocity when we write ratio of linear velocity to radius, we can say the linear acceleration become v square by r. So when a positive charge q moves with velocity v in a normal magnetic field of b Tesla, moving charge particle will have magnetic force equal to qvb sine 90, as this 90 degrees angle between velocity and magnetic field, and magnitude of magnetic force become qvb, and this force act normal to displacement which is along velocity, and when force act perpendicular to displacement or velocity, it results in a circular motion, and during this circular motion the particle have a radial centripetal force equal to mv square by r, and particle will stabilize its circular motion of a particular radius according to its velocity, charge and magnetic field flux density by the balance of magnetic force and centripetal force, and during this circular motion a reaction centrifugal force of mv square by r balances with centripetal magnetic force qvb, and due to that balance this revolving particle from this central axis maintain a constant radial distance and revolves in a uniform circular motion. Now this balance of inward magnetic force and centrifugal force mv square by r results in radius of circular motion given by mv upon qb, where m is mass of moving charge particle, v is linear tangential velocity of charge particle, q is charge of moving particle, and b is existing normal magnetic field flux density, and the product of mass and velocity is known as linear momentum. So we can say the radius of uniform circular motion of charge particle in magnetic field is linear momentum divided by product of charge and flux density. So for a constant velocity and constant magnetic field flux density, the radius of circular motion is proportional to ratio of mass to charge of moving particle, and for a given particle particle and given magnetic field, the radius of circular motion directly proportional to velocity of moving particle. If we increase velocity of moving particle, the magnetic force increases, but centrifugal forces increases in a square proportion, and to maintain equilibrium of magnetic force and centrifugal forces, the radius of circular motion of moving particle will get doubled proportional to the doubled velocity. Now for the constant velocity and given particle, the radius of circular motion is inverse proportional of magnetic field flux density. That means if we increase magnetic field flux density, it will increase centripetal inward magnetic force, and to maintain the same amount of centrifugal outward forces, the radius of path will decrease and generate an equilibrium, and in that equilibrium, radius of uniform circular motion is inverse of magnetic field flux density. When the velocity of moving charged particle and existing magnetic field are normal to each other, the moving charged particle will experience maximum magnetic force QVB, and the direction of force all during uniform circular motion as given by Fleming left hand rule by the direction of thumb is perpendicular to velocity or displacement of moving particle, and when force and displacement are mutually perpendicular, the force won't produce any work on moving particle, and the kinetic energy of moving particle or the magnitude of velocity speed remains the same during this uniform circular motion of moving charged particle in a normal uniform magnetic field. During uniform circular motion of charged particle in normal uniform magnetic field, magnetic force always exists on moving particle, and this magnetic force produce acceleration, and due to that acceleration the linear tangential velocity of particle changes, but that change will be only in the form of direction and there won't be any change in magnitude. So during uniform circular motion, the linear momentum and linear velocity of particle changes in direction, but there won't be any change in magnitude of linear momentum or speed. If a positive charge is accelerated by a certain accelerating potential V, and work done by electric accelerating potential QV become its kinetic energy, so kinetic energy of particle E become half mv square, and this is work done on charged particle by accelerating potential. In our physics study, the relation of kinetic energy and momentum is very important. So to relate half mv square energy relation with momentum, we multiply this relation by 2m, and when 2me is done, it become m square v square, and m and v product is linear momentum. So this become a famous relation of linear momentum and kinetic energy, p square equal to 2me, or we can say the momentum of particle product of mass and linear velocity is root 2me, and if kinetic energy of particle is achieved by the work done of accelerating potential, so charge q accelerated by accelerating potential v will have kinetic energy qv. So in place of kinetic energy we can write qv, and momentum become 2m qv square rooted. And we know in uniform circular motion, when magnetic force QVB become equal to centrifugal mv square by r force, then the radius of circular motion is given as mv upon qv. Mv is linear momentum, so radius is given as momentum divided by product of charge and magnetic field flux density. In place of linear momentum we can write root 2 me, and radius become root of 2 me divided by qb. And if kinetic energy is attained by accelerating potential v, then in place of kinetic energy we can write qv, and our relation for radius of circular motion will become root 2m qv divided by qb. Now this can be simplified as 1 by b multiplied by root of ratio of 2 mass accelerating potential divided by charge. So we got different relation of radius of circular motion in terms of particle velocity, particle linear momentum, kinetic energy of particle, or accelerating potential before coming to normal magnetic field. And according to the conditions given, we can make calculation of radius of circular motion using appropriate relation. This numerical example will explain selection of appropriate format for numerical calculation. We have given that a charged particle having mass 25 milligram or 25 into 10 to the power minus 6 kilogram has a charge 100 microcoulomb. Now this particle is accelerated by a potential difference of 5 kilovolt, and after that acceleration it enter normally to a uniform magnetic field of 2 Tesla, and we have to find out radius of uniform circular motion in magnetic field of that charged particle. When initial velocity and magnetic field got a 90-degree angle, the particle will have maximum amount of magnetic force given as QVB. Particle perform a uniform circular motion and centrifugal force mv square by r get balanced by radial inward centripetal magnetic force, and from this equilibrium force relation the radius is given as mv divided by qb, where m is mass of particle, v is velocity of particle, q is charge of particle, and b is existing normal magnetic field to velocity in Tesla. Now in place of velocity of particle, we are given accelerating potential of particle, and accelerating potential got a relation with kinetic energy of particle. So in place of moment P, we can write root of 2me, and in place of energy, when we write charge multiplied by accelerating potential, this root of charge with this charge when simplified will give us the radius relation as 1 divided by magnetic field flux density multiplied by root of 2 times mass and accelerating potential divided by charge. Now for this numerical example, existing magnetic field is of 2 Tesla, mass of particle is 20 milligram or 25 into 10 to the power minus 6 kilogram, the accelerating potential is 5 kilovolt, and the charge of particle is 100 microcoulomb. Here this 2 multiplied by 5 become 10, and 10 multiplied with 10 to the power plus 3 and 10 to the power minus 6 become 10 to the power minus 2, and in denominator side 100 multiplied by 10 to the power minus 6 become 10 to the power minus 4, and this square root calculation is 50, and 50 divided by 2 will become radius of uniform circular motion of charged particle 25 meter. This conventional textbook example is very popular examination question pattern, and it has 4 different conditions. We have given that 3 particles, proton, neutron and alpha, enters in a uniform normal magnetic field and perform uniform circular motion on 2 different paths. We have to find out those 2 particles which follows the same path, and we have to state that path and those particles. So in first condition, all 3 particles, proton, neutron and alpha, have the same velocity before they enter in uniform normal magnetic field. Now we know that in a normal magnetic field, when velocity and magnetic field are mutually perpendicular, the magnetic force is QVB maximum, and equilibrium of 2, magnetic force QVB and centrifugal force mv square by r gives me radius of circular path as ratio of mv to qb, where m and q are mass and charge of moving particle, v is its velocity, and b is normal magnetic field. Now all 3 particles got same velocity, they are entering in the same magnetic field, so the radius of circular path become proportional to ratio of mass to charge of moving particle. And in proton we have 1 protonic mass and 1 unit electronic charge. For neutron we have 1 proton and 1 neutron, 2 mu mass and 1 proton charge. And in alpha we have 2 proton and 2 neutron, total 4 mu mass and 2 protonic charge. So this ratio become 1:2:2. That means neutron alpha would have the same radius, twice of that of proton. So here this path 1 of larger radius and smaller curvature is followed by neutron and alpha. So here neutron and alpha will follow the same higher radius path 1 in this uniform normal magnetic field, and proton will follow the path 2 of smaller radius. In this example, 3 particle, proton, neutron and alpha, with the same linear momentum p, that is product of mass and velocity, enters in a uniform normal magnetic field and perform uniform circular motion of 2 different paths, and 2 particles are on one particular path and the third particle is on another path. And we know in a normal magnetic field, the radius of circular motion is given as linear momentum divided by product of charge to magnetic flux density. And as all 3 particles got same linear momentum and are in the same magnetic field, so the radius of circular path become inverse of charge of moving particle. And for 3 different particles, proton, neutron and alpha, the ratio of their radius inverse of their charge is, charge of proton is 1 unit, charge of neutron is also of only 1 unit, and charge of alpha is of 2 unit. And when we take LCM, the ratio of radius of proton, neutron and alpha become 2:2:1. It means proton and neutron will follow identical path of larger radius and smaller curvature, that is 1, and alpha will follow this second red path of smaller radius if all three enters in a same normal uniform magnetic field with same momentum. In this third example, again three particle proton, neutron and alpha enters in a normal uniform magnetic field, but this time they have the same kinetic energy. So in normal uniform magnetic field, a moving charged particle perform a uniform circular motion, and the radius of that circular motion is given as ratio of its linear moment to product of charge and magnetic flux density. Now in place of linear momentum, we can write root of 2 times mass and energy. And since all three particles got same energy and are entered in the same magnetic field, then this radius of circular path become proportional to root of mass divided by charge of moving particle. And for three particle proton, neutron and alpha, the ratio of radius is given as, for proton, mass is 1 unit and charge is also 1 electronic charge, and for neutron, having 1 proton and 1 neutron, mass is 2 unit and charge is only of proton 1 unit. So this become root of mass to charge. And for alpha, 2 proton and 2 neutron, mass become 4 unit and charge is 2 protonic charge. And when root 4 is solved as 2, this ratio become 1, and the ratio of radius of proton, neutron, alpha enter in a normal uniform magnetic field with same kinetic energy is 1 is to root 2 is to 1. It means the two particle proton and alpha follow the same path of smaller radius, that is this red 2 number curve, and neutron will have a path of higher radius and smaller curvature, that is 1. In this fourth and last example, three particle proton, neutron and alpha are accelerated by a electric potential of V volt, and after acceleration and attainment of kinetic energy, they enters in a uniform normal magnetic field with 90-degree angle position and perform circular motion. Now the radius of circular motion is ratio of linear moment of moving particle divided by product of charge and flux density. In place of linear momentum, we can write root of 2 times mass and energy, and energy of the charged particle comes from accelerating potential, and when a q charge is accelerated by v potential difference, the amount of work done by accelerating potential qv will become kinetic energy of moving particle, and this relation is simplified. Then for same magnetic field and same accelerating potential, the radius of circular path become proportional to root of ratio of mass to charge. And for three particle proton, neutron and alpha, proton got 1 unit mass and 1 unit charge, and neutron got 2 unit mass, 1 unit charge, and alpha got 4 unit mass and 2 unit charge, and this ratio simplified as root 2. So three particle proton, neutron and alpha perform uniform circular motion after acceleration from same potential difference will have a ratio of radius 1 is to root 2 is to root 2. It means the two particle, neutron and alpha, both have same ratio of mass to charge and higher than that of proton. So neutron and alpha will follow path of higher radius, that is path 1, and proton will have path of smaller radius. When a charged particle of mass m and charge q enters in a uniform normal magnetic field of b Tesla with velocity v, it will perform a uniform circular motion of radius r, and the time period of that circular motion is time taken for one revolution in circular orbit, and with r radius, the periphery of one circle is 2 pi r, and with linear velocity magnitude v, the ratio of displacement to velocity is time taken for that displacement, and all through the motion, the magnitude of velocity, that is speed, remains the same as perpendicular magnetic force to displacement never perform work or change its kinetic energy. And in place of radius, when we write ratio of linear momentum mv to product of charge and flux density, then this velocity will get cancelled out, and we'll found that the time period of circular motion doesn't depend upon velocity of moving particle, and it is 2 pi m over qb. And for given magnetic field flux density for different particles, the time period is proportional to ratio of mass to charge, and in all particles the electron got least mass to charge ratio, so it has least time period of circular motion, and neutron and alpha got identical mass to charge ratio, so they have the same amount of time period in circular motion in a particular magnetic field. Now the frequency is inverse of time period, and when we invert this time period relation, then frequency become proportional to qb upon 2 pi m, and this q by m is known as specific charge, and for electron and positron the value of specific charge is maximum. So during circular motion in uniform normal magnetic field, electron and positron will have highest value of frequency in circular motion, and deuteron and alpha particle got same specific charge amount, ratio of charge to mass, so they will have also the same amount of frequency. And both expression of time period and frequency clearly indicate that the time period or frequency of circular motion doesn't depend upon velocity, kinetic energy, or accelerating potential before entering in magnetic field of charged particle. This particular concept of time period or frequency of circular motion of a charged particle in perpendicular uniform normal magnetic field is very important. The expression of time period is 2 pi m upon qb, where m is mass of particle and q is charge of particle, and inverse of time period is frequency, is the ratio of qb to 2 pi m. And both expression of time period and frequency clearly indicate that they will not depend upon velocity of moving charged particle or momentum, energy, or accelerating potential before entering magnetic field doesn't influence the time period or frequency of circular motion. It is mainly decided by the magnitude of working magnetic field and the ratio of mass and charge of moving particle. If same particle enters in a uniform normal magnetic field with increased velocity, the radius of circular motion increase proportional to velocity, and a particle moving with higher speed will have higher radius of circular path, and the travel time to complete one revolution will become the same, as radius of circular path and velocity of particle are proportional to each other. This example will clear all our doubts and explain the concept of time period and frequency calculation for uniform circular motion in magnetic field. We have to found the ratio of time periods of circular motion in uniform normal magnetic field for proton, deuteron, and alpha. And this question to be done for 4 different conditions. All 3 particles would have same velocity, or in second case same linear momentum, or in third case same kinetic energy, or in fourth case all 3 particles should be accelerated by same potential difference, and after acceleration through that potential difference they enter in normal uniform magnetic field to perform circular motion. So in all 4 conditions we have to find out ratio of time period of proton, deuteron, and alpha. So we know that time period is ratio of linear periphery of circle 2 pi r divided by speed of moving charged particle, and radius is proportional to velocity of moving particle, and relation of radius is mv to qv, and time period calculation will cancel velocity from numerator and denominator, and it become 2 pi m over qb, and this relation doesn't depend upon velocity, linear momentum, kinetic energy, or accelerating potential of moving particle performing circular motion, and time period of circular motion is proportional to ratio of mass to charge. And for proton, deuteron, alpha, the mass of proton is 1 unit, mass of deuteron is 2 unit, mass of alpha 2 proton and 2 neutron is 4 unit, and the charge of proton and deuteron is 1 unit, and charge of alpha is 2 unit. So this ratio is 1:2:2. So whatsoever velocity, momentum, energy, accelerating potential difference, the 3 particle proton, deuteron, alpha in the same magnetic field will perform circular motion with time period ratio 1:2:2. We hope this learning video has informed each and every aspect of uniform circular motion of charged particle in magnetic field, and you understand how the radius of circular path depend upon velocity, linear momentum, or kinetic energy of moving particle, and you could also understood the time period or frequency of circular motion of charged particle doesn't depend upon velocity, energy, or accelerating potential of charged particle. It only depend upon mass and charge of moving particle. Our other learning video of this playlist are equally useful for your exam preparation, and if you need our online doubt clearing classes or exam centric dedicated notes, do join our YouTube membership. Thank you very much.